Okay, we've done a lot of work with doing some math with solution calculations. Let's talk a bit conceptually about what these solutions look like and what's really happening. So, in many of these things, what you're doing is you're taking something. Like, let's say you have NaCl, where the Na gets represented as a little plus molecule and the chlorine with a minus molecule. And then what you do is we're adding these into water. And you'll notice, like if you put salt into water, make boiling water to cook pasta or something, the salt looks like it disappears. Now, if you go and you taste the water, don't do this in lab. But if you're cooking, that's fine. The water will taste salty, more salty if I put more sodium chloride in it. Now, technically, if you add enough sodium chloride, eventually you'll just get a pool of salt at the bottom and it'll stop dissolving. But for a while, you can dissolve a good bit of salt into your water if you really want to. That's how you get like the ocean that tastes like salt. Don't go drinking ocean water, please. But ocean water, right? It's pretty salty. It's well known for that. So clearly, the salt goes somewhere. It doesn't just disappear into thin air. It doesn't like evaporate or something. So what happens is when we add it into water, we get a setup. I'll draw it bigger. What happens is the parts break apart from each other. So I'm a bad drawer. My goal was to treat it like the solid version I was adding, the stuff here. This plus and minus are connected to each other exactly. So they're attached. When I put them in water, and I drew them too big so I can't easily show it, they separate from each other. And then what happens is water molecules will get attracted to them instead. So imagine these things here are water molecules. So my little poorly drawn triangle represents our hydrogen, oxygen, and hydrogen. And as a reminder from our chapter on polarity, this oxygen is going to be a little bit negative, and these hydrogens are going to be a little bit positive. Well, hey, that's why we actually studied all that polarity stuff. The negative part will be the pointy end. It's going to point at the positive stuff that gets dissolved because it's got a side that's negative. It's going to want to be next to other positives. So these water molecules come and surround your particles that were originally a solid that got made up when they get dropped in the water. So we end up with all these little negative charges around the positives and partial positive charges around the negatives. So these get broken up in water. Now, this is not true for all solids, even all ionic solids. Some ionic solids, you put them and they drop like a rock to the bottom. So what's important is if they are soluble, that's what this case is. That's the soluble case. If they're insoluble, they will stay as solid and not be dissolved. So this is the language we use. If they're dissolved, we say they're soluble. If they can't dissolve, they're insoluble. If they're insoluble, they'll be at the bottom. So if we take something like, let's say lead chloride is an example of a solid that won't dissolve in water. So if we add some lead 2 chloride, we just get a block or powder or whatever solid form you added of your lead 2 chloride just sits at the bottom. It just goes, you just drop it in the cup, it goes, boop, lands on there, just stays there. You can shake it up, it's just going to stay there. You might disturb it a little bit, the little particles might float around for a second, but then it'll fall down to the bottom because it doesn't dissolve. At least not very much. In 1212, you'll talk about itty bitty bits that dissolve. But for the purpose of 1211, we just talk about things either mostly dissolve or mostly don't. And we're going to stick to that level of explanation. So lead 2 chloride basically won't dissolve. Almost nothing of it will dissolve. It'll fall like a rock. Sodium chloride, unless you add a tremendous amount, will dissolve in water. As we know, we cook with it, or some people cook with it. You may not cook at home, but if you do, we add salt to water a lot to cook with. So, a term I want to mention, there's going to be a term we use for this. So, things that dissolve in water will also cause that water to be able to carry an electric current. So, we're going to use the term electrolyte for something when added to water. When added, we'll just say when added, allows electricity to flow. So, you put salt in there, it dissolves. It's an electrolyte, so it's going to ease how easy it is for electricity to flow. Now, technically, there's a measurement of that, right? It's not just it flows or it doesn't. If there's enough energy trying to push it through it, most things you can eventually get electricity through. Not every. Some things are really good insulators, but the more difference there is where we really want to get electricity through. Depending on the substance, it can be either easier or harder to get that through. You will talk about that in great deal in physics, the concept of resistance and how we know how hard is it to get through something. How does an insulator work? That's a whole other section of science. It's neat. I like it too, but we're not going to deal with it here. We're just going to say, I put certain solids in. If they dissolve, because they're ionic compounds, they're going to be electrolytes. That means they're going to let electricity flow when we put them in. On the other hand, if I put them in, if they don't dissolve, they can't be an electrolyte. Or if when they dissolve, they don't break apart into a positive and negative part. For example, sugar also dissolves in water. Sugar is a compound, though, that doesn't have a positive and negative part like sodium chloride does. Sugar just dissolves as sugar. It stays sugar in water. So it's not going to help the electricity flow because it doesn't break apart and create these charged particles that help the electrons flow. So electrolytes are going to be substances that when you put them in water, break apart into these separate positive and negative parts. These will be ionic compounds. For in this case, so this is one example of how we work with it. So sodium chloride, as we learned back in our naming compound sections, Na+, Cl-. They stay together, but there's still a positive and negative that are attract each other because of electrostatics. You put them in water, they get separated, they're an electrolyte, they allow electrons to flow more easily. You put sugar in water, sugar is not ionic, sugar just stays sugar, and it doesn't help the electrons flow. So, how do I figure out, though, that lead-2 chloride, I knew it was a block, and I knew sodium chloride dissolved. How do I know that? We're going to use some rules. Now, I'll note, for my classes, I give you these rules on your test. It's about being able to apply them, depending on who you have. Some people don't do that. I think over time, you'll learn the ones that are really useful, and the ones you can't remember too well, it's not too hard to go look up. Also, we expand on these later to talk about, well, what if something kind of dissolves but kind of doesn't? So, here is our table of rules. Now let's talk about how to view it, and I'm going to shrink. I need to go away. We're going to have me disappear because I'm blocking some of the rules. There we go. Bye, everybody. I'm still here, even though my face isn't there. So, the top half of this little section up here, what these are, this is for compounds that are usually soluble, so they usually break apart. So on the left side, you have the ions that are very soluble, things like lithium, sodium, potassium. On the right side, you have the only exceptions of what's not going to dissolve. So for example, I said that lead-2 chloride, my PbCl2, was going to be a rock if I put it in water. Well, chloride is usually soluble, but lead-2+ is an exception. So if lead-2+ or mercury or silver are attached to chlorine, bromine, or iodine, they'll actually form solids, even though usually they would be able to dissolve in solution. The bottom half are usually insoluble, so our hydroxides, our sulfides, our carbonates, and our phosphates, and they have these exceptions over here. Now I'll point out one thing about reading this table is your hydroxides and sulfides have 3 categories. The reason for this, for the purpose of solving problems in this class, we're going to treat the terms slightly soluble and soluble the same, but that's not really quite true, and in 12.12 we'll go into detail of what that might look like, or not what it does look like. But for example, calcium hydroxide, CaOH2, is slightly soluble. What that means is you can put a little bit in and you'll get it to dissolve, but you won't be able to get a tremendous amount. Everything else we're dealing with, when we say it's soluble, you can get a fair amount in. Now, what the word fair amount means still changes based on your substance. Some substances are still easier than others. But this pair, these hydroxides, are both very relevant because they make bases, which we'll talk about next week and in some future videos in this chapter. And they're really relevant, and they only get a little bit to dissolve. So this can come up from a practical perspective. That's why it gives this slightly different term. But for the purpose of saying, if I put this in solution, do I get a solid or not? I'm going to treat soluble, for the purpose of asking questions, as slightly soluble, and soluble is the same thing for that. But purely practically speaking, and what you'll deal with in 12.12 is that's a borderline issue. So now, let's take a look at some examples of how to use this table. Because as obvious as it may sound, I do definitely see people that get into trouble because they try to use this table and they manage to do so incorrectly. So I want you to pause me and take these 4 compounds and identify, are they soluble or insoluble? And then I'll go over it once you've done that. Now let's talk about this, and hopefully you took that moment to work on these. So we start with PbCl2. Well, I already told you that that is insoluble, which means it forms a solid. So reminder, insoluble means solids. Soluble means aqueous. Now second, you have CuCl2. Well, chlorine is usually soluble. There's no exception for copper. So CuCl2 is going to be soluble. Now, I also know it can be annoying because S is solid and soluble starts with an S. So I'm going to write out a few letters like INS or SOL. Then we get to calcium nitrate. Nitrate is listed as usually soluble and it has no exceptions. So we're going to say this one is soluble. You then have barium sulfate. This one is down here. And if I look, barium is 2 plus 2 is an exception. So this is going to be insoluble. Now for a fifth example, just to show what it might look like for something else, let's say I had KOH, potassium hydroxide. Well, hydroxide is usually insoluble, but it's listed as an exception that is soluble. So it's going to be soluble. Also, KOH, you could have looked up top and used the rule of the fact that potassium always dissolves. Some substances, both ions are going to show up, and they'll give the same answer. Some substances, only one ion is going to show up, and you'll have to look for that one. So you need to be comfortable with looking at both the cations and the anions, because depending on your substance, it might only occur in one place. For example, calcium carbonate. The top, I don't have any Ca plus 2 plus rules, but I do have CO3 2 minus down here. It's usually insoluble. It's not listed as an exception for carbonate, so that would be insoluble. So that's how you go about solving these. Now, let's see. So the last thing we want to do is we want to talk a bit now about how to use this to predict chemical reactions. So I'm actually going to have to make a new slide and grab this to go with it. So you're going to see my workflow for a second. Woo, copy this, make a new slide. I have nothing interesting, thankfully, to show you. My desktop is not particularly interesting. So now, let me get this back, make a writer. So let's say we took some potassium carbonate that was aqueous and we reacted it with some nickel 2 chloride. Nickel, that's also aqueous. And we want to know, does this make a solid? So conceptually, how do we figure this out? Well, first we have to go to our reactants, and if they don't tell us, we have to check and see if they're aqueous. So in this case, they are. What this means is you have two beakers. One beaker has some K pluses and some CO3 2 minuses. Beaker's kind of small, hard to fit it. The other beaker has some nickel 2 pluses and some chlorine minuses. So inside their own beakers, we'll go they're not going to make a solid because those substances are aqueous. So as long as you only have nickel and chlorine around each other and potassium and carbonate around each other, they don't make a solid. So what we do though is we take both of these and we dump them together. Now they could be in two separate beakers and you pour them in, or it could be something where you've got one beaker and you add the other substance. Both work. So we mix them together and now we have four things. We have some K pluses, we have some nickel 2 pluses, we have some carbonates, and we have some chlorines. And we need to know, do any of those form a solid? Because any of the pluses could react with any of the minuses. Now you don't have to check plus and plus, and you don't have to check minus and minus, because those aren't going to be attracted to each other. But we've got to figure out, do they form solids? The way we're going to do this is we already know potassium with carbonate doesn't make a solid. Nickel with chlorine doesn't make a solid. So we don't have to worry about those two sets. We only need to check the potassium with the chlorine and the nickel with the carbonate. The way we do this is we're going to flip the anions in our balanced chemical equation. So I'm going to say, what if, instead of potassium being with carbonate, what if it was with chlorine instead? So K plus and Cl minus, that's a 1-to-1 ratio, so we have KCl. In the other case, what if my nickel, that's 2 plus, reacts with my carbonate, that's 2 minus? Well, then I would have nickel carbonate. So now we flipped the two anions. This makes it so they're with different cations, and we're going to check each of these and see if either of them makes a solid. If so, we've got a precipitation reaction. We formed a solid when we mixed together two aqueous things. So if I look up my rules for Cl or K, K has no exceptions. Cl doesn't have an exception for K, so this is going to be aqueous. Now the nickel carbonate, on the other hand, if we look up carbonate down here, it's usually insoluble, and nickel is not one of its exceptions. So this is going to make a solid. That means when I mix these together, I'm going to get a solid to form. So if I wanted to write out the balanced chemical equation, I would have K2CO3 aqueous plus nickel 2 chloride aqueous reacts to form KCl, and the KCl part is aqueous because it dissolves, but then the other is nickel carbonate, and it's a solid. So now this is my balanced chemical reaction. Well, it's not balanced yet. When we balance it, we have to put a 2 in front of the KCl. So if you're not sure how to do that, go through and look through it. You can actually balance all the atoms, but if you put a 2 in front of the KCl, you'll have 2 potassiums, 2 chlorines, 1 nickel, 1 carbon, 3 oxygens. All the atoms will be balanced. Now, this only has a reaction if something forms a solid. If the answer were both were aqueous, what you would say is no reaction occurs, because you've mixed together 2 containers of floating around ions, and then if none of them dissolve, none of them form solids, they're all 4 just going to sit around and float in solution. Nothing changes. You just mix them together, but there isn't a chemical reaction since they were floating around at the start and they were floating around at the end. This case, though, is a chemical reaction because the nickel carbonate comes together and forms a solid. So now, let's get a second example for you to try now. So I want you to try this one, and then we'll go over it. So let's look at sodium nitrate plus lithium sulfate. I want to know, these are both aqueous. I'll just go ahead and tell you. Is there a chemical reaction? And if so, what's the balanced chemical equation for it? So pause me and give this a try. Okay. So we're going to switch the anions. That means our sodium plus is going to pair up with the sulfate 2 minus. So if I do that, I'm going to get Na2SO4. If I look up my rules, sulfate is usually soluble and sodium is not an exception. So that's aqueous. And we're also going to combine our lithium plus 1 in our NO3 minus 1. So that'll give us lithium nitrate. Lithium and nitrate both have no exceptions, and they are both soluble. So this is aqueous as well. Therefore, I can say no reaction occurs. This one does not have a chemical reaction because everything is already balanced. Not balanced, but everything's already dissolved, and it stays that way. So nothing happens. You would just write no reaction, and you would move on. So this finishes up our rules on solubility rules. After this, we'll have one more video for this week where we're going to look at some ideas of how to write these equations in different ways.